Hello again. Here's part two of review sheet number 3 of the third unit of physics from last fall. Now, I feel a little guilty about doing so much review and overemphasizing third law on this review because I think there's just one question on the final exam about this. But at least going over it might improve your chances of getting that question right. So let's get started. I've shown 3 forces acting on the backpack. And remember, you draw the force arrows on the object feeling the forces. So we want to identify the reaction force to each one of these. So let's just go ahead and start without me kind of re-explaining third law again. So let's start with force of hand. So that represents the force of the hand on the backpack. As you can see with that red arrow, the hand is pulling up on the backpack with 20 newtons of force. So here's the question. Where do I draw the force arrow? How big is it and which direction? Well, if that's how hard the hand is pulling up on the backpack, how hard is the backpack pulling down on the hand? 20 newtons. And so there is a force, excuse me if I don't have the right length here, of the backpack pulling down on the hand. They come together. It's like there's one force that the hand and the backpack share, and that's 20 newtons. They're pulling on each other with 20 newtons. So the force of the backpack on the hand equals 20 newtons down. Does that make sense? All right, let's do the normal force. And what I mentioned in the previous review, the previous part of this review sheet, is think of the normal force as force of some surface on that object. So that represents the force of the ground on the backpack. That's what normal force is. It's the get away from me force. And so that's how hard the floor is pushing on the backpack. So then how hard is the backpack pushing on the floor? 40 newtons. So here's a little yellow circle which represents the floor. And so this is the force of the backpack on the floor. And that is 40 newtons. They're equal and opposite. They push on each other with 40 newtons. And finally, probably the trickiest, is the weight of the backpack. Remember that represents how hard the earth is pulling down on the backpack. That's the weight, the force of Earth's gravity pulling on the backpack. So I'll restate it again. If this represents how hard the Earth, planet Earth, is pulling down on the backpack, well, how hard is the backpack pulling up on planet Earth? 60 newtons. So here's planet Earth, not to scale, I hope you know that. And so that represents the force of the backpack on Earth. And that is 60 newtons. So I won't say much more about it, but that's the idea. That's how you think about it. All right, let's get to number 24, another calculation problem. And as I was trying to establish on review sheet number 2 and in part 1 of this review sheet, success on doing kinematic problems, and even here in mechanics problems, that combines actually mechanics, things with forces, with kinematics, things involving motion and velocity and acceleration. It just comes down to identifying what's given to you, writing the symbols for those. Don't underestimate how to write the symbol for each of these. And then now that you're armed with the symbols of everything in this problem, you just look for the equation that will help you solve it. So I'm going to do it 2 ways. I think the original answer key, I was doing it the way that we had practiced a while, that we were using both delta x equals v average t and delta v equals at in 2 steps. Actually, we'll need more than 2 steps for this problem since there's a net force to solve the problem. But remember, you're going to be armed with all 4 of those main kinematic equations, so you get to the answer a little more quickly if you recognize which of those 4 equations works best, and you could solve it, at least part of this problem, in 1 step. Okay, you'll see what I mean once we start this. I'm going to do it the shorter way by using 1 equation to solve for something that we'll need to solve for here. But then I'll go back and do it the other way kind of quickly, because again, I'd rather you, at this point in your career, to just do it in 1 step now that you know all 4 equations. Okay, here's what we do when we get a calculation problem. Don't make this more complicated than it needs to be. I'm going to write down all the things that are given to me and what I'm being asked to solve for with their symbols. In fact, I'll go ahead and put the numbers. If you're in a hurry during the final, you don't need to bother with the numbers, but it will help you to write down what each one represents. So that right there, what do you think that represents? It's slowing down from 50 meters per second to 10 meters per second. So that represents the initial velocity. Actually, I'll put in the numbers in a second because we might want to, well, I will go ahead and do it now. It looks like I really don't have to worry about positives or negatives here because everything is kind of in the same direction. But I'll just go ahead and call the direction that it's currently going the positive. So it's originally 50 meters per second. What does that represent? The final velocity, VF. 10 meters, same, it just slowed down, it didn't change directions, so it's still positive if we're calling that direction positive. What does this represent? Well, in physics, we really don't use d, distances, it's all about displacement. So the displacement is 150 meters, and kind of implied, of course, it's in the same direction. It can't be in the opposite direction if we've been always going in the positive direction. And what is it looking for? It's looking for sigma F, the net force. Okay, we're not going to find a single equation that has all those things in it, our standard equations that we memorized or that you wrote down for your final exam. So we'll get to this kind of in the last step, but that's going to be our clue. If we're going to be solving for net force, we have one single equation we've been using, right? And that's net force equals ma. Now, we're given, oops, I forgot to write that up there. I just realized that. Back over here, of course, that's the mass. Of course, that's not the weight because I'm using kilograms. So since we have the mass and we're looking for the net force, what does the problem come down to solving for? Dangling my preposition there. We need to solve for A, right? So again, this is what you do in physics problems. You see what's given to you, you kind of strategize a little bit about, okay, what do I need to do? So now it all comes down to using this information here to find the A, and then once we do that, we can use the mass, we can use the A that we solved for to solve for the net force. Does that make sense? I know it's not easy. I mean, you guys are doing really complicated problems for 8th grade, so be kind to yourself if this is not particularly easy. It shouldn't be easy. It should be a little bit challenging. Okay, so let's do it with a single equation. What I've been talking about is, look what's given to you. V initial, V final, and delta x. So you'll look at your list of equations and say, and we're looking for A, right? So we want to find some equation that has V initial, V final, delta x, and A in it, because we're going to be using that equation to solve for A. And this is that fourth equation we learned. We didn't practice it too much, but I hope it's not too difficult once you've identified the equation to solve for it. So that is V final squared equals V initial squared plus 2 times A times delta x. That has all four of those things in it. Time doesn't appear in here, which is great because we're never given the time in 24. So let's go ahead and plug them in. And because we're not doing DESPA here, even though it says practice or DESPA for the final, I won't even bother with the units. We're going to trust that as long as we have the right equation and we're using SI units everywhere, we're going to get the SI unit for acceleration automatically. So V final is 10. So again, excuse me for not putting units. V initial is 50. The acceleration is what we're solving for. And the delta x we said is 150. Okay. So I'll just show my work a little bit. 100 equals 25. What's that? 2,500, right? Plus 300a. Okay. Now we're going to move the 2,500. I guess we'll do that. And so this will become negative 2,400, right? Moving the 2,500 to the opposite side equals 300a. And therefore a, you could do this in your head, is negative 8. And then what should acceleration be if I'm consistently using SI units everywhere? Meters per second squared. There we go. It's not that, I shouldn't box that. Yeah, I solved the A, but I forgot we need to go to the net force. So we'll say that's temporarily our answer. So now we just need one more step. Net force equals, not that I have to show this work, but that's how we're going to get the net force, which is what it's asking for. So the mass was 1,000 kilograms, right? Yeah. It's a little bit light for a car. And the acceleration is negative 8 meters per second squared. And so it's negative 8,000. Hey, let's remind you something. Now, literally putting those units in, we're going to get kgm per s squared. But what does that equal? Not that you have to do this, but you should recognize what that is, because maybe on the choices for the answer on the multiple choice question, I'm not going to write kgm per s squared. So what is that equal to? Well, that's equal to a Newton. So you can say that the net force is negative 8,000 newtons. And it's negative. So maybe on the final, I'll have one possible choice of being positive 8,000, and maybe that'll be choice A, and you'll be tempted to immediately circle it because you recognize 8,000, or you forgot to get a negative there. So be careful. So I suggest on all these calculation problems where you have multiple choice, see if there's a positive and negative version, because maybe I'm trying to trick you there. Okay, really quickly, what if we didn't want to use this equation? We wanted to use our two original equations of V average, delta x equals V average t, and delta V equals AT. Well, you can. And again, just as a reminder, even though I'll prefer that you do it the simpler way, saves you time. Remember, I've been saying this multiple times, whenever you're given an initial and final velocity, you could solve for two things. You can find V average, and you can find delta V. So how would we go about it if we wanted to use just those original two equations? Well, notice I'm given a delta x, and I could use one of these to solve for something else. What could I pair with delta x to solve for something that we don't even have in this problem? I could use delta x and V average to solve for t, which is not even given to us. So let's try that, and we'll see where we're going to lead with this. So again, not that you have to show your work, but delta x equals V average t, or t equals delta x over V average. And so the delta x is 150 meters. And let's practice this in our head. There could be a simple problem, I bet there is, where I'm just going to give you some initial and final velocities and then either ask for V average or delta V. It could be. It's just not, I don't have a lot of room to ask a bunch of questions on the final. So this is pretty easy. What's the average between positive 50 and positive 60? 30, right? So 30 meters per second. So you know me, I always like convenient numbers. So 5 seconds. So now we have the time. So if we have the time and we're trying to get to A, do you remember there's an equation that allows us to relate all those? Yeah. So A equals delta V over T. So we're going to put in that 5 seconds, but we now need to find the delta V. So if it started 50, now be careful here. We start at 50 and we end at 10. What's the change? Not 40, negative 40, right? And then when you do that, you get negative 8 meters per second squared, which is what we got before. So I won't finish the problem. Now you just plug it into net force equals ma. So that's kind of a cool thing about physics is that often there are multiple ways of getting to the answer. Unsurprisingly, because remember those two other equations we learned later in the semester, they come from the original two equations along with the equations for that and that. But again, I prefer that, at this point, you kind of find the easiest way to get to your answer. But for those of you who like to find your own creative ways, we could have found it with those two equations. Okay, sorry that took a while, but again, I think a lot of you were a little bit nervous about being ready for these calculation questions. All right, let's try 25. And not that I'm going to say this on the final exam problem, I'm not going to tell you, use this equation, but I was trying to force people to practice this equation because we got so used for the second unit and the beginning of this third unit of only using this equation and that equation. I kind of want to get people used to choosing some other equations. But we can see, let's practice, let's say that I didn't give that to you, and I just gave you the problem. Again, let's do that technique of writing down what we're given and then figuring out what equation we would use. So we start with an initial velocity. I won't bother, no, I guess I will because it might have a positive or negative here. The initial velocity, we throw it upwards at 30 meters per second. I think most of us would just say, go ahead and put that positive. So now we're calling up positive, right? So keep that in mind. This is the tricky part here. With an acceleration due to gravity of 5 meters per second squared. So it's on another planet, it's not Earth. So I'm going to write A because the acceleration due to gravity, which we use little g to specifically represent, is just the acceleration, A. But the acceleration due to gravity is always down. So if I'm saying up is positive, because I said throwing the ball up is positive 30 meters per second, the acceleration is negative 5 meters per second squared. And I said the time is 4 seconds, and I'm looking for where it will be. So in other words, what is delta x? Of course, it's always implying where will it be, not necessarily to the ground, but wherever it was initially had 30 meters per second. So maybe that's from your hand. So where will it be compared to when it left your hand? So again, pretend like I didn't give you this. You would say, well, I have V initial, I have A, I have T, and I'm looking for delta X. You would scan through your equations and you'd say, oh, there's an equation that works perfectly. This one, that's the third equation we learned. So let's go ahead and do it. Hopefully it's convenient numbers. V initial is 30. I'll just leave, sorry, I shouldn't be doing this, but we're just hurrying up a little bit. Time is 4 seconds. Should always put your units. Okay. If I'm not going to put my units, I won't put a unit for there either. The acceleration is negative. That's going to be a big difference in an answer, whether I put negative or positive there. And then T is 4 squared. So again, apologize for my sloppiness. That's going to be 120 from that first term. And then 16, which is 4 squared, times 1/2 is 8, times negative 5 is negative 40. And so that's going to be 80. And then we're doing SI units here. So what do you think the unit's going to be for this? Meter. So build your confidence. I bet you can do these. And don't panic if it takes you a little bit. We cook that into the time. We know that a lot of the multiple choice should take you well less than a minute. So if it takes you 3 or 4 minutes to do that, I think you'll be okay on the time. All right, 26. Now, I'll go ahead and say this. I'll just give it away. Hopefully I'll remember to tell you this in class, because I know a lot of you won't be watching this video, is that I'm not going to put any of these two problems where we learned Coulomb's law, which is the electric force due to charged particles, or Newton's gravitational law there. I know we have the F sub g equals mg for the weight, but that's kind of a shortened version of that one, where little g represents this times this divided by that squared. So anyways, I'm not going to do it, but in fact, I'll go ahead and do it really quickly, just if you're wondering what the answer is. All you would do, well, I changed my mind again. I'm not going to re-record this video. Sorry for my my sketchiness there. But all you would do is put in the value of k, and I'm looking here. I guess I'm relying on you to look up the value of k somewhere. Actually, this is a different problem. Okay, I could ask this maybe, or the one with gravity. So again, excuse the fact that I'm being all scattershot here with my thinking. But let's go ahead and do that problem. But I was saying that I'm not going to give you one where you're plugging things into the equations for the Coulomb's law or Newton's law of universal gravitation. I don't think I'm going to give you one like this, but again, I haven't looked at the final recently, so I think I'm not going to ask you, but let's go ahead and do it. Sorry about the delay. So let's try this. If the electric force between two charged objects is 5 newtons, what will be the force if I give one of the objects 10 times more electric charge, but make the distance between them 5 times farther away? So notice how the electric force depends proportionally on the electric charge, which is like Q1 or Q2. So if I'm starting at 5 newtons and I'm making one of the Qs 10 times bigger, the electric force is going to be 10 times bigger. So we'll be up to 50 newtons, right? Now I'm making the distance 5 times farther away. So first of all, if I'm making the distance greater, I'm increasing the distance, should the force go down or go up? Well, as you are used to with the electric, any kind of force, greater the distance, the weaker the force. So this better go down, right? Should be less. But is it going to go down by a factor of 5? No, remember, it depends on d squared. So if I make the distance 5 times farther away, how many times weaker will be the force? The force will be 25 times weaker. So we're going to end up with 2 newtons. Okay. I'm not trying to be coy again. I just don't remember if I ask one of those. So I think it's not too hard, especially when I use nice, convenient numbers like that. But save some time, since I wasted so much time butchering what I was going to do for 26. We'll skip 27 because I'm not going to ask you to plug it in. It's not hard. You just plug in this value for each M1 and M2 and divide by that squared. Just being careful that we're using proper units. Like if I told you centimeters here or something, we'd have to convert it to meters. If you're doing it and you don't have the answer key in front of you, just looking at the answer key myself here, you would get 0.06 newtons. But I won't ask that on the final. Similarly, I won't ask this problem here. I'm going to ask you a friction problem like I did earlier somewhere here in this, was it there? Yeah, there, something like that. But I'm not going to ask you anything with these, from that lab we did, what did friction depend on? It's just been way too long. I don't want you to have to try to remember what happened there. But if you're curious, the answer for these two questions is kinetic friction, moving friction, does not depend on the speed. But it does depend on the normal force, how hard that object is being pressed against the surface. But again, I'm not going to ask that, so be okay. Also, we didn't spend a lot of time practicing this. I feel a little guilty. We just kind of learned it and then moved on. It's not a big topic for us, so I'm not going to ask that. So I'll just skip that. And just to save a little time again, I'll let you look at the answer key if you want to know what the answers are, but don't bother looking at it. I always look at that and think it's some kind of dirty word, but I'm not sure why. Anyways, let's get back to the last big topic, which is going to be the rest of this lab sheet. And I think you guys got pretty good at these, or really good at these. But again, it's been a long time, and it's one of these skills that we didn't keep up. We kind of learned it and then moved on in Unit 4, never really coming back to momentum or impulse. So let's go ahead and do this, this problem here. And if you don't mind, I'm going to take a drink here of my soda to keep me awake, and then we'll get started. I'm going to ask you guys, what did I do in the middle of my video to see how many of you guys are listening to this? I know some of you are. You're such good guys. What is the momentum of, okay, let's just start. I'll do a little mini lesson. Let's find a blank spot down here. I don't need too much of a mini lesson. I'm just going to remind you of some formulas and some ideas. So momentum, we use little p, and it's just mass times velocity, not weight, but mass times velocity, which will be important for this question that we're about to do. I won't say much about that. It's a vector, so it has a direction, so it could be a momentum to the east, up, positive, negative, whatever. So that might be an issue later. But we're about to get some problems that involves impulse. And impulse, there's not really a universal symbol for it. It's one of these weird things, but more often than not, if people use a symbol for impulse, it's capital J. And there are two ways of thinking about impulse, just like for the next review sheet on Unit 4, when we get to energy, we'll have kind of two ways of thinking about work. We kind of wrote an equation two different ways. One way to think about impulse is it's just the change in momentum. So the terminology people often use for impulse is you provide an impulse to something, or something receives an impulse. So whatever the change in momentum is represents the impulse that you provided to the object. So if the object, like a shopping cart, is stopped and I push it to get it going and give it some momentum, whatever that change in momentum is the impulse I am provided to the object. So that's one way of thinking about impulse. But another way about thinking about impulse, I'll just rewrite it as a second equation, is it is equal to the force that you apply times the time that you apply that force, assuming you're just going to do a single force. Now, not to confuse you, but next review sheet for Unit 4, that kind of looks like another one. Work is force times distance, but force times time is the impulse. So one way to find the impulse is if you know the force and the time, you know the impulse that you're providing. So if I'm pushing with some, 20 newtons for 3 seconds, multiply 20 times 3, and you get 60. That's the impulse. And the unit there would be Newton seconds, or as we'll see, kilograms times meters over seconds. And again, the other way you can find impulse, you have to be flexible, is if you can find out what the change in momentum was, you know the impulse. And some problems, we kind of use both to solve it. So that's about all I want to say, except for, again, getting back to the units that we get. So make sure you have all these written down on your sheet, and you should have some success. Again, I think there are about 15 questions or so on this unit here. So at most, there might be 2 questions, possibly 3, on momentum or impulse. So don't be too worried about it. Okay, let's get back to number whatever we were. Okay, number 29. What is the momentum, P, so it's asking for P, right, of a 100-pound kid? What is a 100-pound kid? What is that? Is that the mass? No, that's the weight. We're, again, probably in junior physics, you're going to see that they use a W for that. But I just trying to be consistent where all my forces were F sub something, so force due to gravity. So we're going to have to deal with that. And then he's running at a constant velocity there of 5 feet per second. So we're looking for momentum. And so momentum is just the mass of the kid times his velocity. All right. So that says mass. That's my little hint there, which again, I will not put on the final. So you have to recognize on your own that that's not mass, that's the weight. So what you're gonna have to do, and this is one of the times where I didn't use a convenient number, is go from weight to mass. And that's a skill that actually people kept having a little trouble with this. I think they kept forgetting the difference between the two and how to use this equation. So F sub g, the weight, is the mass of whatever that is, times the acceleration due to gravity on that planet. And we'll go ahead and use 10. And the reason why I used 100 is I was trying to trick people to think, oh, this must be the one where I'm dividing by 10, because he always likes to use convenient numbers. Nah, I caught you. So let's solve for the mass first. It's his weight divided by little g. And so that's 100 pounds, which if you want to think about it is, do you remember what that represents? You should know these things for the final hint, slug foot per second squared. Now I'm going to divide by the acceleration due to gravity. So notice I'm using imperial stuff here. So I shouldn't use 10 meters per second squared. I want to use 32 feet per second squared. And so that's going to cancel that. And what are we left with as our units? Slug, right? So this is, again, one of those things that didn't turn out to be very convenient. I'll just fit it right here. It's about 3.1 rounding off a slug. So that's the mass. Let's solve for the momentum. The momentum is going to be 3.1 slugs. I always say slug for some reason instead of slugs. And then times the velocity, which is 5 feet per second. So when you multiply that, you get 15.5. And what's the units? Well, again, you're totally okay to leave it as it is. You just multiply those two units and you get slug feet per second. But just so you're a little flexible, that's going to be the same thing as a pound second. And I don't know if I could kind of show you that, but maybe I'll save some time here by not going that. But that's just going to be a pound second. I'll show you really quick because you might be curious. You don't need to really know this. But a pound, as I just wrote up there, is a slug foot per second squared. So what do you think a pound second is? A pound second is a pound times a second, right? Which means this cancels the squared and you're left with slug foot per second. So those two things are the same. You can write it both ways. And again, be a little flexible because I might, on an answer key give you one rather than the other, and you just have to, not the answer key, but the choices for the multiple choice give you one or the other. So slug foot per second is a unit of momentum and for impulse, as we'll see later, which is the same as a pound second. All right, this will go a little bit faster, I think, for most of it, because I kind of explained most of what I was going to explain. What is the velocity? So we're looking for V of a 0.15 kilogram baseball. That's the M. Okay, so that's kind of what you do in physics problems, just kind of identify what's given to you. Not that it's always going to be obvious after that, but it helps you. If it has that many units of momentum, so that's the P. Okay, we have P, we have M, and we're looking for V. What's the equation we're going to use? P equals mv. So we're looking for velocity, so velocity is going to be P over m. The momentum is in SI units now, kilograms meters per second. And the mass is 0.515 kilograms, which of course is the mass there. It's not the weight. And when you do that, you get, I'll just fit it down here, 40 meters per second, because the kilogram cancels the kilogram, and we get meters per second. All right. So maybe just kind of revisiting the units, I told you that for imperial units, those are the two versions here of the imperial unit for momentum, or as we'll see, for impulse. And then the two versions of momentum or impulse for SI, as we just saw right there, is a kilogram meter per second or a Newton time a second. And we often put little dots there so it doesn't look like someone's trying to write plural of newtons or something. Not that you ever should or would, but often we separate units with a little dot. I think you're used to that. All right, You change the momentum. Ooh, that sounds kind of familiar. Where did I hear about change in momentum? Oh, okay, we're talking about impulse, right? So probably we're going to use impulse here. You change the momentum of an object from 4 slug foot per second. Okay, that's the imperial unit for momentum. To 9 slug foot per second. What impulse did you provide? And this is a really easy question, but again, you're just not used to this. So it sounds like something complicated, but just remember impulse is your capital J, and you'll have written down that J, impulse, is equal to the change in momentum. In fact, going back to when you, sorry to get you dizzy by going up and down, when you write that on your review sheet, maybe just put like a little in parentheses so you know that's what that represents, because we didn't get a lot of practice with that. J is impulse. So if there's a question that says, what's the impulse? You can see on your note sheet that we're looking for capital J. So J, impulse, is just the change in momentum. Final momentum minus the initial. That's always change, final minus initial. So I'm not going to write those down. What did it change by? 5 slug foot per second. Or if I wanted to write this, maybe I need it, maybe I don't, 5 pound seconds. And it's positive. It went from 4 to 9, so we changed by 5. Now we want to stop it. So here's like a classic question I kept asking. We want to stop some object to figure out what impulse you need to provide or what impulse it needs to be given. We need to stop it. So what kind of, I can't think what I'm talking about. What does its momentum need to be at the end? It needs to be 0. So don't get confused by this 5 that we just solved for. We got it up to 9 slug foot per second. So it's starting, we can say P initial, not that you need to write this, as 9 slug feet per second. Okay. And we want the final momentum to be 0, right? This is overcomplicating. This is actually quite easy. So what do we need to do? What do we need to change the momentum by? That's the impulse that we need to give it. We don't need to change it by 9 slug foot per second. Change is always final minus initial. We need an impulse of, which is the change in momentum, of negative 9 slug feet per second. Okay. So I think you got used to that idea that to stop something, you just need to provide an impulse that is equal to the momentum it currently has, but opposite sign. So I could try to trick you. Let's say that something had an impulse at the end of, a momentum at the end of negative 10 slug feet per second. So somehow we were just defining the direction such that it has a momentum of 10 slug feet per second. And I want to know what impulse I need to provide in order to stop it. Well, what's the answer? Positive 10. Okay, I don't mean to try to confuse you there, but that's the idea, is you just need to provide an impulse to stop something equal and opposite to the momentum that it currently has. I hope this comes back to you and you are feeling comfortable. An object is going west with 40 slug feet per second of momentum. So that's P, or P initial, right? You push on it with a force of 10 pounds to the same direction it's going for 3 seconds. What will be the new or final momentum of the object? Well, first of all, without even bothering with the west, I was just doing that to be sure that you understand which way I'm pushing on the object. If something's going to the west and I'm pushing with a force to the west, is it going to have less momentum or more momentum? It's going to have more, right? So whatever we get here, we're going to be adding some momentum to the 40. Okay, I won't write down all the sort of DESPA stuff and write down what we're given. We just need to know, I'll at least write this. That's the force I'm applying, and that's the time. So do you know an equation that has force and time in it? Yeah. The impulse is the force you exert times the time that you're exerting the force. So we're going to exert a force of 10 pounds. I'm doing a lot of imperial ones on this problem set. 10 pounds times 3 seconds. 3 seconds, sorry about that. So I'm going to apply an impulse of 30 pound seconds. And again, don't freak out. That's the same thing as a slug foot per second. I did that purposely, so that it looks like they're mismatched units, because we're going to need to add this. But just realize a pound second is the same thing as a slug foot per second. So without worrying about too much, remember that the J is, not worrying about showing our work too much, the impulse is just the change in momentum. And so if we're going to apply or give it 30 pound-seconds of impulse, we're going to either increase the momentum of this by 30 or we're going to decrease the momentum by 30. Well, as I just explained a little while ago, we're pushing it in the same direction that it's going, so we're going to increase its momentum. So our final is going to be 70 either pound-seconds or slug foot per second. Same thing. So that's kind of like one of the quote-unquote complicated problems we were doing here with impulse is you had to use both equations. You had to think of impulse as your force times the time. And then once you get that, you have to realize, oh, that's just going to be the change in momentum that the object is going to experience. So it's not difficult. It's just, again, we didn't get a lot of practice with doing that. We had like a few problem sets where we did those, and then we had the test and we moved on. 33. A 1,000-kilogram car is going 10 meters per second, positive direction, when we slam on the brakes, which supply a negative 2,000 newtons force. Of course, the force will have to be in the opposite direction that we're going in order to slow down the car. What impulse is needed to stop the car? So this is actually a little trickier. So remember the impulse represents the change in momentum. So what will be the momentum of the car when it stops? 0, right? So to figure out the impulse we need to provide to the car, we have to know what the initial momentum is, because we need to know the initial momentum so we can know the impulse. I'm kind of trying to think of what I'm going to do here. So we need to know the initial momentum of the car. Momentum is mass times velocity. So I conveniently gave you mass, not weight. So we got 1,000 kilograms times its velocity. It's going along at 10 meters per second. So nice and convenient. We got 10,000 kgm per s. I'm going to just go for the fun of it, write that as a Newton second, just to remind you that a Newton second is the same as a kgm per s. Okay, so that's the car's momentum, and it is positive because the velocity was positive. Now, to stop it, what impulse do we need to provide to the car? That's kind of the opposite of number 32 there that I was talking about, actually number 31b there that I was doing. So what impulse do I need to provide? The impulse I need to provide is negative 10,000 newtons times seconds, right? And that'll get rid of all the momentum. So now we're going to, that's the answer, just to make sure we answer that question right there, is now we're going to say, how long will it take to stop the car? So the J is the delta P again, right? So, but that's also equal to F times T. So we can say that the time that it takes to stop the car is the change in momentum or the impulse, which is going to be equal to that impulse or the change in momentum over the force that you're applying. I'm just solving that for time. And so the impulse again is, keep that in there, negative 10,000 Newton seconds. And here you can see why I changed kilogram meter per second to Newton seconds, because we're going to plug in here the force that's being applied by the brakes, negative 2,000 newtons. And what cancels? The newtons. And what are we left with as a unit? Seconds. And it better be because we're solving for time. And in fact, the negatives cancel, which better because we're not going to get a negative time. So you get, again, that's me. I always like convenient numbers, 5 seconds. That is tricky, okay? And again, like I said, maybe 2 or 3 questions combined on momentum and impulse. I'm guessing. I wouldn't be surprised if it's just 3. Number 34, you are catching an egg. You have a choice between catching the egg over 0.1 second, you're stopping it really quickly, or over 0.2 seconds. You're kind of letting it fall and slow it down as you maybe moving your hand down as you're catching it. When you use the longer time, what does that do to each of these things? The impulse you provide. Nothing. It doesn't change it. Because remember, the impulse is the change in momentum. Whatever momentum the egg has when it reaches your hand, you need to stop it. So you need to get rid of all the momentum that the egg has as you're catching it, right? So you provide the same impulse to the egg, whether you're stopping it in a short time or stopping it in a long time. But the impulse depends on both the force and the time. J equals F times T, right? So the J will be the same whether you're doing 0.1 second or 0.2 seconds for the time. But if j is the same, the product of F times t has to be the same. So if I'm using a bigger t, 0.2 seconds, what does that say about the force that I'm going to be applying? It's going to be half as big compared to the force I would need to do over 0.1 seconds. I know that's not an easy explanation, but the idea is the longer we could extend the time, make t bigger, F can be smaller. And that's why, for example, I guess what's popular now is to play hacky sack, is if you're trying to catch the hacky sack on your top of your foot, you kind of bring your foot down as you're catching it, because you don't want a large force on the hacky sack. It'll just bounce off your foot. You want to slow it down gradually and have a small force on the back, the hacky sack. So as it's reaching your foot, you extend the time that you are providing the impulse, slowing it down to a stop, and that makes the force on the hacky sack smaller, and it just doesn't bounce off your foot. Okay. Almost done. A 0.3 kilogram ball, that's the M, not the weight, is going 40 meters per second to the north. Let me get rid of this so I don't get confused. So that is V initial, just identify things. When it's hit by a bat and switches to going 50 meters per second to the south, that's V final. And we said, oh, what impulse was provided? I'm not sure if I really need to write all those things, because we're just going to end up using those two equations, or one of them at least, to do this. So we have impulse, if it's asking for impulse, that's J, and think about delta P. Why am I saying right now, think about delta P and not thinking about force times time? Well, in the problem, am I giving you anything about forces or time? No. So evidently, we're going to be solving for the impulse by finding out what the change in momentum is of this ball. So we're going to be careful with the signs here. Let's find the initial momentum, which is m times the initial v. And that's going to be 0.3 kg times 40 meters per second north. Let's go ahead and call north positive. Okay, why not? So we're going to get 12, meters per second. We're going to get 12 kilograms meters per second. Now, what's the final momentum? It's the mass times the final momentum, which is still 0.3 kilograms. Now, the final velocity is going to be 50 meters per second, but it's going to the south now. And if we went ahead and said north is positive, what's the final velocity? It's going to be negative 50 meters per second. So this is going to be negative 15 kgm per s. Again, sorry about my handwriting. So remember, whenever you find change of whatever, it's the final minus the initial. And use parentheses if you want to worry about anything like a negative minus, minus a negative or something. But I don't think we have to worry too much here. We take the final, which is negative 15, and we subtract the initial, which is positive 12. So we have negative 15 minus 12, negative 27 kgm per s, or Newton seconds. So again, not hard, but again, we didn't have a lot of practice. So here we were just looking for the change in momentum, and that represents the impulse. All right. These last two are conservation of momentum problems. And I think I will put one of these on the final. Again, I'm not trying to be coy, but it's a skill that is very useful. Whenever you hear things colliding and they give you initial and final velocities and masses and stuff, immediately think of conservation of momentum. That's where when you do collisions, that's kind of what momentum is used for. So let's go ahead and write down the given information. And I'm actually going to draw a little diagram. Sometimes it helps to do that. So I'm going to go ahead and maybe erase some of this stuff to create a little space. I'll draw the diagram up here. Okay. So we're going to have to be careful of directions and signs. So we have this golf ball. I'm going to draw the golf ball here. And I'll go ahead and put above that the mass is 0.04 kilograms. And it's moving at 3 meters per second. So I'm going to say it's moving this way at 3 meters per second. And it's going to strike a 0.25 kilogram billiard ball moving towards it. So it's going to be heading to the left at 1 meter per second. So I'll draw the billiard ball a little bigger at 0.25. Is that right? Yeah, kilograms. And then it's moving towards it at 1 meter per second. Right. So let's solve this. We want to know, and afterwards, that's the before. We can draw the afterwards. The golf ball is, I don't. at least we'll get started here, and then we'll think about it afterwards. I just don't want to get too messy with all these diagrams and confuse you. So the conservation of momentum is what we're going to do to solve this. So in other words, the total momentum at the beginning is going to equal the total momentum at the end. In fact, we wrote it like this. The sum of the momenta initially, which I said like at time 1, must equal the sum of the momenta at time 2. So we're going to add up all the momenta, or the 2 momenta, of the balls at beginning, and that must equal the total momenta of the 2 balls at the end. So let's be careful of signs here. Let's go ahead and say that that direction is positive. Okay. So remember, momentum is just mass times velocity. So without writing an equation here, what's the momentum initially of that ball? Well, it's 0.04 kilograms. And I think what I did for this is I said, not that you have to show your work, but just to see that the units work out. I'm taking the mass of that ball in kilograms, and it's going 3 meters per second to the right. But still on this side of the equation, I'm adding the initial momentum of the other ball. So the other ball is 0.25 kilograms times -1 meter per second, because we're saying to the right is positive. Now, maybe also, again, I don't want to confuse you by drawing another diagram down there. You could, many people do, is after they collide, I won't be so greedy. Let's go ahead and draw it. I'll use up some of your time here. After they collide, the golf ball is moving at 7 meters per second in the other direction. That's 7. And it says, calculate the velocity of the billiard ball after the collision. Okay, maybe that's another reason why I didn't do that. Here's the billiard ball. We actually don't know which way it's going and how fast. We're trying to find out that V. Is it that way? Is it that way? I don't know. So I guess it didn't help us too much, other than the fact that, yes, the golf ball is going in the opposite direction that it was. So that's the negative direction, right? So let's go ahead and do that. At the end, the golf ball is still 0.04 kilograms. Its direction is to the left, and it's going 7 meters per second. So that's -7 meters per second. And then we're going to add the momentum of the other one at time 2. And so that's 0.25 kilogram times, I don't know. That's the one thing we don't have. So let's erase this. And so we have a little room here. Of course, you're not showing your work on the final. So I just wanted to do that. Usually I had you do that to make sure all the units kind of match. We're using kilograms and meters per second everywhere. And I told you for these, just to relax our constant use of imperial units, let's keep it more scientific and use SI units everywhere. So let's rewrite this more simply without all the units. It'll look a little bit better. So we have 0.04 times 3 plus negative, we'll go ahead and multiply this. In fact, we'll go ahead and do that there. What's 0.04 times 3? 0.12, and I'll leave out the units. Plus -1 times 0.25, and in fact, since we end up negative, I'll just put a negative there. That'll be negative 0.25 equals 0.04 times -7. That is going to be negative 0.28 plus 0.25 V. Okay? So adding these, we get, I'll erase this a little bit later, negative 0.13 equals negative 0.28 plus 0.25 V. Move the negative 0.28 to the other side, that'll be positive 0.28, and we get 0.15 equals 0.25 V. Divide both sides by V, and we get 0.15 over 0.25, which is 3/5, which is equal to 0.6. And we assume that it's going to be meters per second because we're solving for velocity using SI units. Now, it's positive velocity that we got. So after the collision, I erased my figure here. Which way did the billiard ball end up going? To the right, right? Because we defined that as the right. So that wasn't the smoothest explanation I've ever had for a problem. Sorry if that wasn't completely clear. But whenever you have a problem where you have two objects colliding and we're giving you masses and velocities, this is what you're going to do, right? And all you do is add up the momentum of the two objects beforehand and set that equal to the momentum of the objects afterhand. And then there's going to be one thing you don't have to do. And yes, don't bother writing the units That's the one part I kind of regret. I'm not going to record this, is we're not showing our work. So just put in numbers, making sure. I'm not going to try to fool you on the final and give you one that's in kilograms and meters per second and the other one being in grams and centimeters per hour. I'm going to be nice and just give you kilograms, meters, and seconds everywhere. So if you don't put units, you're going to be fine. But pay attention to the direction. That's the one mistake people make, is understand which way it's going, to the left or the right, and do positive or negative appropriately. All right, let's do one last one. How sad we're ending this worksheet. It's actually not that bad. I mean, it's interesting topics, but it's just a lot to review before the final. So this is another conservation of momentum problem, because notice I have things colliding, and that's immediately the thing you're going to think, oh, I'm going to be doing conservation of momentum. We didn't get to this, but when you get to junior physics, you're going to also probably combine this with changes in kinetic energy. But we just kind of kept it more simple and just said, let's just do conservation of momentum here. We hadn't learned about conservation of energy or kinetic energy at this point last semester. So we have a ball of clay heading to the left at 6 meters per second. When it collides with another ball of clay traveling to the right at 6 meters per second, they collide and stick together. What is the velocity of the stuck together clump? Maybe you don't have to do this, but in fact, I recommend not doing it for the final. But just so you can visualize it, here is our 2 kilogram ball of clay, and it's saying it's heading to the left at 6 meters per second. Again, I'll just leave out units. And when it collides with a 4 kilogram clump of clay, heading to the right at, also 6. Okay, they're both going 6. That's the before, I'll put B, and after, they stick together afterwards. So maybe I should draw a bigger clump. They kind of stuck together, made one big lump of clay. And we want to know what the velocity is. I'm not going to be sure which way it's going, but we're looking for that velocity. Okay, which way do you want to call positive? I think we all have a tendency, since we read left to right, we'll call right positive. It doesn't matter, but we'll just call that positive. So we do conservation of momentum. You don't need to write this, but just the idea that we're going to sum up the momenta of both objects before, and that's going to equal the momentum after. So let's get going. I won't write units to make it more streamlined here. What's the momentum of that ball initially? Well, it's the mass 4 times its velocity, which is 6, and that's the positive direction. Then we're going to add to it the momentum of that ball. Well, the mass is 2, and what's the velocity? -6, right? And then that's going to equal the momentum at the end. Now, here's the big difference between this and number 36. In number 36, they stayed separate. There are 2 objects before, 2 objects after. Here, you form one merged object that is stuck together at the end. So we just have one object moving left or right. So we need the mass of that lump of clay when they stuck together. What's the mass? Well, the sum of the masses. It's 6, right? And then what's the velocity? Well, that's what we're solving for. And we don't even know if it's left or right yet. We'll find out once we solve it. So this is going to be 24 minus 12 equals 6v. In other words, 12 equals 6v. Or the velocity equals 2. And what do you think the unit is? Meters per second.